Okay, so welcome everyone. Welcome back to this year's of the Combinatorics Seminar. So the standard time will be at 11:30 a.m. in Australian Eastern Daytime currently, and at least you have found the way at the right time, so that's good. I hope you had a great break, and it's my great pleasure that we have Rosie talking today, who was moved from last year, and that we finally found a common date, and then this is happening. So she's talking about Surrounding Cops and Robbers, a vertex-pursuit game, and I should have said she's currently at the University of Canterbury. So it's all yours. Thank you.
Thank you. Kia ora koutou. So this is all work that has been done with this long list of co-authors, and as I was saying just before, they're all in various places in Canada. So I started this project when I was doing a postdoc in Newfoundland, and then it was published just last year. So I'll be talking about surrounding cops and robbers. So if I can change the slide. So I'll start by briefly introducing the traditional or original cops and robbers game. So it's a vertex-pursuit game that's played on a graph. So if I'm playing on this path here, I'm going to try and annotate my cops and robbers because they need to move. So first of all, the cops start by placing themselves somewhere in the graph. So maybe a cop starts here, and then the robber places themselves somewhere, and then the players alternate. So the cop moves, and he's going to move closer to the robber. So here, and the robber's going to run away because he wants to avoid capture. So the robber might move here, and then the cop continues to chase until eventually the robber has ended up at the last vertex, and then the cop captures them by landing on the same vertex. So the cops win the game on the graph if they can occupy the same vertex as the robber, and the robber wins if they can forever evade the cops. So we may need more cops for the cops to win. So if we play on the cycle graph, we can see that if I just have one robber and one cop, the robber would keep moving around the graph, evading the cop. So we would need a second cop, and they would start. The cops would place themselves, and then the robber might place themselves here. But you can see that the cop would just move around and sort of capture the robber. First they move here, and then they can capture the robber by landing on the same vertex. So in a cycle, if we have just one cop, then the robber can keep running away forever. So the robber would win. But if we have two cops, then the cops will eventually capture the robber. So we use the cop number to denote the minimum number of cops that are required to guarantee capture. So we saw before that we could capture the robber with just one cop in the path, but for a cycle, when we looked at the cycle, we needed two robbers. So really when we're talking about cops and robbers game, that's often the question we're really focusing on is what's the cop number of a given graph. So we can look at other graphs. So in the complete graph, wherever the cops place themselves, wherever the cop places themselves, wherever the robber places themselves, they're only one edge away from the cop, so the cop's going to capture them in the next round. So the cop number for the complete graph is 1. And then we can investigate other types of graphs. So for the Peterson graph, we actually need 3 cops. And you could kind of think of this as playing 2 cops play on a cycle, and then you have a third cop chasing the robber out of the other cycle. You could think of this as an inner cycle and an outer cycle. So if the cops place themselves here and here, and maybe one in the center, the robber might think about where do they want to place themselves. Obviously not on a vertex that's adjacent to a current cop. So let's say they place themselves here. Then my two cops on the outer circle would move closer to the robber. And that was it. So they might be here and here. That will force the robber to move in here. And then my remaining cops are going to keep chasing. So eventually, it's a cop. They're going to keep following. So robber's moved in here. This cop would have moved over here in that move. And now the robber's again adjacent to a cop. So he needs to keep moving. Maybe here. But in this move, now my other cops outside can move in here, and this guy will move in here. And my robber again has to move outside. And so now this cop that's now here can move here, and this cop can move here, and this one can actually just capture. So on the generalized Peterson graph, we need 3 cops, and it gets a bit more involved once we start getting more interesting graphs. But that's the general idea of the cop number.
Rosie, there's a question in the chat. The question is it true in general that for any 3 regular graph, the cop number is 3?
I don't think so. I've got a result later on where I talk about the minimum degree. So I might.
Yeah. There's a comment that actually K4 has cop number 1, so that's already.
Okay. I might just check that I can see the chat. There we go. Yes, thanks, Robert. So in general, a generalized Peterson graph has been shown to have cop number 3 or 4, and then there's been some work on determining which case is which, but that was in 2017 by Ball and others. So sometimes you need 4 cops on a generalized Peterson graph, but that's as bad as it gets. So the cops and robbers game was introduced independently in 1983 and 78, but it was originally introduced as just thinking about 1 cop. So if I have 1 cop, which graphs are cop win, and which graphs can the cop win against the robber? But then in 1984, these people introduced the idea of the cop number, of how can we increase the number of cops and what's the minimum number we need to win. And then if you're interested in looking up the cop number, or there's a whole lot of different variants on the cop number, there's a really nice monograph by Bonato and Novakoski that looks at a whole lot of different aspects. It's a really nice survey of the cop number. But I'm talking today about surrounding cops. I'm going to mostly be focusing on that variant of the cops and robbers game. But before we get there, I want to introduce Meyniel's conjecture, which states that for any graph, the cop number is big O of square root of n. So this conjecture is really nicely encapsulates, can we get this really nice upper bound on the COP number for any graph? And that's still an open problem, although there are lots of results on upper bounds and different classes of graphs. And I'll as I introduce some of the results that we came up with in our paper, I'll be referring back to the COP number and comparing with some known results from the COP number. But really, this is one of our aims in looking at the COP number, is to find this upper bound. I see there's a question from Svetlin come through about whether the cops and robbers can see each other. And yes, we are assuming that everyone can see what everyone else is doing. So yes, is the answer to that question. There are variants of the game where I think there are variants where the robber can see where the cops are, but the cops can't see the robber. Or there are variants where the robber knows what the cops are going to do next, but not the other way around. So there are variants that explore who can see, who has what information, or whether the cops or the robbers move in different ways. There are variations where they play on the edges instead of the vertices. But I would refer you, for those sorts of questions, I would refer you to the survey, that monograph. So we're looking for an upper bound on the COP number, and we found a few simple examples. So we've seen the complete graph has COP number 1, and you can just think about a complete graph, and if you put a COP on any vertex, it can in one move just capture a robber on any other vertex. The complete bipartite graph has COP number 2. You can put one COP in each part of the graph and they'll be able to capture anywhere that the robber starts. And then the generalized Peterson graph again also has a small COP number. And then there are lots of results that we'll refer to as we go through about graphs from designs, bounds based on minimum degree or CLEAP number and those sorts of things. So for the surrounding cops and robbers, we changed the rules slightly in that we still have the cops move first and then the robber, and then players alternate moves. We still have, everyone has perfect information and can see what everyone's doing. But this time the cops win if they occupy the robber's neighborhood. So what we're aiming for, the robber is here, the cops want to be on either side. So that would be an end condition where the cops have won that game. So you can see on a path that if we play just with one cop and one robber, if the cop places themselves there and then the robber places themselves next to them, in this game, if the cop's then going to move to land on top of the robber. And so for our game, this is not an end condition of the game. In the original game, the cop would have won at this point. But in our game, that just means that the robber is then forced to move. So they then move one place to the right. And then the cop might keep chasing them until they get to the end of the graph, and then the cop moves on top of the robber at the end. Whoops, no, that's not going to happen. If the robber gets to this vertex and the cop lands on top, it's not going to move to the right because that would be capture. It's going to move back again to the left. So one cop on a path that's long enough is just going to keep chasing the robber back and forth, and so the robber will win on a path with just one cop. So we want to be thinking about what is the surrounding cop number. So on a cycle, we move again, the single cop is going to chase the robber around. So if the cop starts here and the robber starts here, the cop might land on top of them, but the robber is just going to keep moving around the cycle forever. So we're interested in the surrounding cop number. What's the minimum number of cops we need so that the cops are guaranteed to capture the robber? Where in this case, by capture, I mean surround, so occupy the neighbourhood of the robber's vertex. So for a path, we need 2 cops. We've seen on the previous slide that 1 cop would just chase the robber back and forth, but 2 cops, if a cop starts, the cops can start anywhere really. If cops start there, I'm going to start using dots for cops and like a 1 for a robber. Maybe the robber starts there. The cops are going to move to the right. Both move to the right. The robber still is going to stay there. But then when the cops move to the right again, now the robber is forced to move. And the place it has to move to is to this end vertex. And so the robber is now surrounded. So 2 cops can now chase the robber to the end of the path, or if they start either side of the robber, they can just zoom in on the robber and capture him. So the surrounding cop number path is 2. Is there a question?
Yes, thanks. So the robber is definitely not allowed to move to a spot where the cop already is. So in that situation where you had 2 cops on neighboring vertices,
yeah,
the robber had to go right.
Yes, so if the, so in our previous position, before the robber moved, he's not allowed to stay where a cop is, and he's not allowed to move to a position where a cop is. So he can't move to this position because there's a cop there.
Thanks.
So that kind of makes it fit as a nice generalization of the original cop number, because the robber's avoiding the cops, so he doesn't want to go where the cops are. But the difference is that if they do end up on the same vertex, like in this position, the robber has the option to keep running away. On a cycle, we also have surrounding cop number of 2. And you could think about even if the cops start next to each other, wherever the robber is, the cops are just going to keep moving around the cycle, and eventually they'll occupy vertices either side of the robber. So the cop number for a cycle is 2. The cop number for the complete graph is n-1. So the surrounding cop number is n-1. For the cop number, we just needed 1 cop to capture a robber, but now we need to occupy n-1 vertices. So it's sort of a really inefficient case because the cops occupy all but 1 vertex, and then the robber's forced to occupy the remaining vertex. And so he's immediately surrounded just by the initial conditions. But if we have n-2 cops, then the robber can just keep moving to the unoccupied vertex. And so for the generalized Peterson graph, we also have, so for the Peterson graph, we also have the surrounding cop number is just 3. And it's a fairly similar process to the cop number algorithm for capturing the robber. They just keep chasing him around the different circles until they end up in the robber's neighborhood. So we've kind of already seen this sort of behaviour before, that the cop number is at most the surrounding cop number. And so we can think of that if the cops are playing just in some graph and they end up in this position where in the surrounding cop number game, they've surrounded the robber, then in the next position, one of them would just move and capture the robber. So if they can surround him, then they can definitely capture him in the original game. So our surrounding cop number gives us an upper bound on the regular or original cop number. So then that leads us to ask, and this is sort of one of the motivations that we had for coming up with this variant, is can our surrounding cop number give us some sort of useful upper bound on the regular cop number? And definitely not all the time, because sometimes we have cases where the cop number is, say, 1 in the complete graph, but it's the surrounding cop number is n-1, or in the complete bipartite graph, our cop number is just 2, but in the surrounding cop number, our surrounding cop number is n. So in order for the cops to win in the surrounding game, they need to start by occupying all of the vertices in one part of the graph. So we can no longer just have 2 cops, but we need n cops for our bipartite graph. So there are some cases where our surrounding cop number is really huge. So in those cases, it's really not a useful upper bound on the cop number. But there are cases where the surrounding cop number is close to the cop number, or a bit bigger, but not a huge amount bigger. And so there's some of the cases we'll be looking at in some of our other results. So one case that's a fairly simple graph, but we have a small difference between the cop number and the surrounding cop number. So in the wheel graph, the cop number is just 1. So the cop is going to start obviously in the central vertex for the original game. And then wherever the robber starts, the cop's going to move and capture him. In the surrounding cop number game, though, the cops can win by starting with 1 cop in the center, and then essentially the remaining 2 cops are just playing on a cycle, because that central cop just stays in the center. And so the 2 cops playing on the cycle capture the robber like they do in a cycle graph. If there were only 2 cops, well, we clearly can't have 2 cops because we know that the surrounding cop number is at least the minimum degree. So 2 cops are not going to be able to capture the robber, because if they imagine they were playing on the cycle and they ended up surrounding the robber here and here, well, he can just move into the center of the cycle, into the center of the wheel graph. So that's one example where we've got some difference between the cop number and surrounding cop number. A tree is another interesting case. So in the cop number, in the original game, the tree works much like a path. So wherever the cop is, the cop may as well start at what I've drawn as the root. If the robber starts anywhere else, maybe the robber starts here, the cop is just going to move down the tree and sort of hem in the robber, and eventually the robber will end up at a leaf and the cop will be next to them and then capture them after another move. In the surrounding game, we need kind of 1 cop to sort of guard a node, and then the other cop acts as a chaser down that node. So if my 2 cops started here and here, if the robber started over in this branch on the left, then my two cops are going to move so that one cop, this guy moves to here, and this guy's going to move, so I'll end up with a cop there and there, which forces my robber to move down, further down the tree, and eventually he's going to be on a leaf. Eventually I'll have a robber on a leaf and a cop here and here, but that robber is surrounded. So in the surrounding cop and robber game, we often need one cop to act as an extra chasing cop, and then the remaining cops act somewhat similarly to the cop number game. And so we see that sort of behavior in graphs like a tree. And we've proved, I mentioned already the result that said that the cop number for the generalized Peterson graph is 3 or 4. We've proved that the surrounding cop number for the generalized Peterson graph is also 3 or 4. And we ran some simulations that found a whole lot of the smaller cases and classified them as to whether they were exactly 3 or 4. But then there's still a whole lot of cases that we don't know whether they're 3 or 4. We had some conjectures around, it seems like there are some smaller generalized Peterson graphs that have surrounding cop number 3, and then from a certain point onwards it starts to look like the surrounding cop number becomes 4, but that's conjecture based on the examples we were able to compute. And I think a lot of that computation and the algorithm work was done by one of the co-authors, Caleb, in one of his summer projects. So that was some really interesting work for him to get into. Another interesting case where the cop number and surrounding cop numbers start to diverge is in the line graph of a complete graph, for example. So the cop number for a line graph of Kn is 1 or 2. And I should have put that as a result, a theorem here, but there's a result that's known that if you know the cop number of a graph, then taking the line graph increases the cop number by at most 1. So that means that the line graph of a complete graph is at most 2. But if we look at a line graph of the complete graph and think about the surrounding cop number, then that's 2 times n minus 2. So I've got a mini example here of a line graph. So a line graph of a graph is, here we've taken our graph K4, and every edge I've represented by a vertex that's adjacent to all the other edges that are adjacent to it in the original graph. So for the surrounding cop number, we know that the surrounding cop number has to be at most the minimum degree, so sigma minimum degree, just because we need to occupy the neighborhood of some vertex. So we know that we need at least 2 n minus 1. We know we need at least the minimum degree of the line graph, but we can capture the cop with 2 n minus 2 vertices, robbers. Sorry, we can capture the robber with 2 n minus 2 cops. So to do that, the robber would start, he would pick 2 vertices in the original graph and then start on all the edges adjacent with one of those vertices, so edge 1 and 4 and 3. So the cops start here and here and here, and then almost all of the edges adjacent to that second vertex that we chose. So edge 2 and 5. hang on, no, not 5, just edge 2. So this is a small example, so the robber doesn't have many choices where he can go, but if the robber has to go on one of these choices, these edges, but then the only neighbour that's not occupied is vertex 5, but the cop on vertex 1 can move there in the first move and surround the robber. So in the line graph, we need at least these many vertices because of the minimum degree condition. But if we have that many cops, then they can move just in one move to surround the robber. So this is one of our examples where we start to see the cop number and the surrounding cop number diverging. So we can also start to think about some different bounds that we can come up with. So we can start thinking about, well, what about subgraphs, or can we modify graphs in some way to get new information? So we might start with these two graphs. So the graph on the left is a subgraph of the one on the right. And so it seems our intuition was, well, if we have k cops in the right-hand graph, we should still be able to capture the robber on the left-hand graph with that many cops. So if we've got a subgraph, is it bounded by the number of cops, bounded above by the number of cops in the original graph? And I've got this example here because actually we need 3 cops in the left-hand graph. We need 3 cops in the left-hand graph, but only 2 in the right-hand graph. I've got a question in the chat. So the question is, does it matter if the cops can move simultaneously or only one at a time between the robber's moves? Yes, it would matter. So in our game, we're assuming that all the cops move simultaneously, as they do assume in the original game. Sometimes though a cop chooses not to move, so staying put is a valid move. So they may choose not to move, in which case it may look like them not moving simultaneously. But generally in our game, they are all moving simultaneously. If they moved at different times, that's going to really change how the game works. I think that will have a big impact on the game. I don't know if there's a variant where that's been looked at, where maybe one cop moves at a time. I'd have to check if that's an existing variant that's been looked at, but we really are assuming that they move simultaneously. Does that answer your question, Peter?
Not completely, because I don't know an example where they're different.
An example, yeah.
It seems as if the examples you showed, you only needed one cop to move.
Yeah, I think it's certainly in the tree. In the tree example, it looked like only one cop was moving, but because they're only moving one edge at a time, both cops actually had to move. I can go back and find.
We can look at it later. It's no
find the tree, yeah. I think the tree might be a good example to look at to check what happens if one cop moves at a time. Also, I think maybe I don't know what would happen in the Peterson graph. That might be another interesting one to look at. But I suspect there would be cases where it would make quite a bit of difference. But I can't give you much more detail off the top of my head right now. So I might go back to this subgraph. In this graph on the right, so we need 2 COPs in the graph on the right. Where they might start is, to give you an idea, if the COPs start, I won't go through the whole algorithm, but basically if the COPs end up so that you've got a COP here and a robber here, and maybe a COP here. So you can imagine wherever you started, you might end up in that position. And I think the algorithm does really have you ending up there at some point. The robber needs to escape from there, and he's obviously not going to move down to this bottom vertex because then he would be surrounded in the next move. So he's going to move up to this top vertex. So the robbers then want to keep chasing. So this robber on the right is going to move down a vertex. And the robber on the left is going to follow the COP up. Now the robber, I think if he moves to the right, then he's going to get captured after a couple of moves by this COP on the left chasing him up, and the COP on the right moves up as well. If he moves to the right, then he's captured in a couple of moves. Actually, I might just play that out. If he moves to the right, then this COP on the left moves up, the COP on the right moves up as well. And now you can see that in the next couple of moves, he's going to be surrounded. Either he stays, he probably wants to stay put, because if he moves up, then the COP on the right is going to move up. So he stays put, and then now the COP on the right moves up and is going to force the robber to move. So the robber has to decide if he moves up or down. If he moves up, he moves into a position where he's surrounded. If he moves down, then my COP on the left moves down and captures him. So there are a few different cases to look at, but the COPs can force the robber to moving into a position where he gets surrounded just with 2 COPs. With the graph on the left, though, if the COPs, if they end up where the robber is on this left-hand vertex and the COPs are either side, the robber's probably not going to start in that position, but you could see that after a few rounds, they're going to end up in that sort of position on one of these corner vertices. So at this point, if it's the robber's turn, he wants to stay put because he can't move to a vertex where the COPs are. If he moves down to this bottom vertex, then the COPs are going to chase him and surround him immediately. So he stays put. So one of the robbers, the COPs then has to move on top of the robber to force him to move. So if this top vertex, top COP moves on to the robber, now the robber has to move up. So he's here, and then it's the COP's turn again. And either, so if we look at this cop on the left, either it stays put, in which case the robber may as well stay where he is, or he moves up. If the robber moves, if the cop moves back up, the robber's just going to move back to its original position. Or if this cop moves up and my cop on the right moves to that position on the left, so we end up like this, then the robber's going to move up again and end up in really the same sort of situation. So the robber, if there are only two cops, the robber can keep traveling back and forth and really just have a preference for staying on these four corner vertices. So as long as the robber keeps moving back to these four corner vertices, he can evade the cops forever. So they really need a third cop. And once you've got a third cop in here, you can see that if it's the robber's turn, at this point he's going to stay put, but the cops are just going to travel around until, so this one on the right will move up, this one at the bottom will move to the right. So we're in that position. And then the cops on the right are going to move up one and be surrounding the robber. So once we've got that third cop in there, we can surround the robber. So these little example graphs show that just by taking a subgraph, that doesn't necessarily give me useful information on the surrounding cop number. So the short answer to that question is no. So if subgraphs don't help us, then is there something like a subgraph that can be helpful? So we look at retract, what's called a retract. And so if H is a retract of G, then the surrounding cop number of H is at most the surrounding cop number of G. So a retract is kind of a way of squinting at a graph. So I have just taken this picture from Wikipedia that took this graph on the left, and if you can see the colours, or they're also represented as numbers, we identify all of the red vertices, get identified just to this this copy of the red vertex in the center 5 cycle. And so we retract this whole graph just into a 5 cycle where we're identifying all of the purple vertices together, all of the red vertices together, and so on. So if we take a retract, then that gives us the retract of a graph has the cop number at most the retract, the cop number of the original graph. And you can imagine the cops playing on the original graph. If they're playing on the original graph, then you could imagine taking those same moves in the original graph and just have them playing in the retract. So if a cop moves from this vertex up the top to something adjacent like that vertex, then in the retract you take that as a cop moving from this vertex or group of vertices to the red vertex that's adjacent. So if the cops can surround the robber in the original graph, then they can surround him in the retract. So that gives us a nice upper bound. It's a similar sort of notion, though not quite as neat as the subgraph result that we were hoping to get. So the proof for that really just was very similar to the same result for the cop number. So it's been shown that the same result was already shown for just the regular cop number for retracts. We've shown a few different bounds on the COP number based on minimum degree. So I've already talked about the minimum degree condition. Can also show a similar result for the clique number. There's a nice result for the girth, relating the girth and minimum degree. So if you've got, if your girth is big enough, then the minimum degree is not good enough for a lower bound. You need an extra COP. And this really nice general result that says you can make the COP number as big as you like in some sense. We've kind of approached a smaller case of that result, relating the girth and minimum degree. And then the tree width is a nice result to compare the COP number with the surrounding COP number. So we showed that the surrounding COP number is at most the tree width +1, whereas for the regular COP number, you only need half of the tree width +1. How are we going with time? So we had also some results on some graphs based on designs. So we found some nice results for incidence graphs of projective planes or resolvable block intersect BIBDs. And then they, just to compare them to the COP number, so for the incidence graph of a projective plane, we needed 1 extra COP than in the regular COP number. For the block intersection graph, so this third point in my theorem, in our theorem, then the COP number is bounded by K, but we needed K times R minus 1 COPs for lambda equals 1. So you can see that there are some differences. I was going to prove the resolvable block intersection, resolvable BIBD result, but I might leave that as an exercise for the reader. Basically, you put COPs on a parallel class and you need 1 extra COP to act as a chaser. So to finish up, some open questions that we were wondering about is exactly which generalized Peterson graphs have surrounding COP number 3, which ones need 4. Other than the graph retract, is there any sort of subgraph or contraction deletion condition that you can do that does not increase the surrounding COP number? And then if you pick a surrounding COP number, can you characterize the graphs that have surrounding COP number K? So for K equals 1, then G has to be just a point or a star. And then finally, our big question is, can the surrounding COP number help to prove Meyniel's conjecture? So we don't really know, but kind of our intuition is that when the surrounding COP number is too big for this conjecture, then in those cases, it seems like the regular COP number is really small. So for example, the complete graph or the line graph of the complete graph. So could we maybe come up with some conditions to look at when is the surrounding COP number close to the COP number? And in those cases, can we use the surrounding COP number to get an upper bound on the COP number? So that's, I'll finish up there, but if anyone's got any questions, I'm happy to answer those.
Thank you very much. Let's all unmute and clap. Thank you. Okay, yeah, are there questions from the audience? Maybe I'll just start with my own question. So that's like some of this, and like the question at the beginning was whether every 3 regular graph is COP number 3, which was 4 because of 4. But then my question was, what about the random 3 regular graph? And so your girth result would say that, well, it's at least 4 for a random regular graph because it has large girth. But so can you think about proving a lower bound on the surrounding COP number, which depends more on the girth?
Yeah, we had mentioned that in sort of our open problems section was moving towards a nice sort of result like there's a really nice result for the COP number, the regular COP number that relates the girth and the minimum degree. So it would be nice to work towards something like that, but I don't know. That's kind of as far as we got.
Yeah, because the intuition is like you put the COP somewhere and the rubber at the other end, and then you're trying to stay far away using the girth. So I don't know. It's just
yeah, that was kind of our intuition too, but that was as far as we got.
Okay, and then the second one, you say when the surrounding COP number is not bigger over root n, then usually the COP number is very small. So the examples you've shown is say like the surrounding COP number is big if the minimum degree is big, right? Like at least the examples you showed.
Yeah, well, the examples I showed.
Is there something where the minimum degree is big? Where the minimum degree is small and the surrounding one would be big?
That's a good question. Once you start getting into some of our, I'll see if I can go back. Some of our design results, maybe not exactly what we're looking for, but you start to see that they're diverging here. If you look at the block intersection graph, the COP number is bounded by K, where our surrounding COP number needs to be bigger. So that's something that's not, doesn't have, that's not quite the same as the complete graph, because the complete graph is in a sense not really a useful example. So there were a few sorts of things around like that, but I can't remember more than that off the top of my head.
Okay, thank you. Svetlana, another question.
Yeah,
Rosie.
a bit of naive question, but when you say that one is small when the other is big, first thing that comes to mind is that there some is bounded by something. Is that true or not?
So just by almost the definition of the game, the surrounding COP number is always going to be bigger than the COP number, or at least as big. So you're trying to use the surrounding COP number as an upper bound on the COP number. So you know that's true. So we don't really know what happens. We're kind of guessing here that we've noticed a pattern in the examples we've seen that when the surrounding COP number is big, really big, then the COP number is really small. I'm not sure if I've answered your question though. So could you repeat it or rephrase it for me?
It might be a difficult question to answer, but again, if two quantities are related in that way that when one is big, the other is small, you think that there some might be, if not constant, bounded by something, say 3 times the number of vertices, whatever. I'm making it up, but some condition like that. Yeah,
that's kind of our intuition, is that there's going to be some condition when that holds, then the two numbers converge. But there are also cases where, for example, the generalized Peterson graph, where the COP number and the surrounding COP number are often the same or really close. And then in some of our graphs based on designs, some of the upper bounds that we had, again, they were really close. So sometimes they're close and sometimes they're far away from each other. So exactly what makes that happen, we don't know. Yeah, so I'm not sure I can really answer your question much more because we kind of were introducing this variant and then starting to explore it in this paper.
There was some other question. I don't know who.
Yeah, Rosie. One of the results for the ordinary COP number is that 3 suffice on any planar graph. So do you have a bound for the surround COP number on planar graphs?
No, I don't. I haven't looked at planar graphs. I don't know if any of my co-authors have thought about planar graphs. But would be an interesting case to follow up. So sorry, that's not a very satisfying answer.
No, it's a great answer. Sure,
Yeah.
it's a good place to look. I suggest you do.
Yes, good place to look.
It's quite possible that that you could get a bound for planar graphs.
Are there any other questions? Doesn't
hi. Well, I have a quick one. Sorry, if you can just repeat the question, the relation between the line graph of G and the line graph of G for the COP number, because I find that quite interesting because it seems very different. Like the game on the graph and the game on the line graph, they look pretty different. So I'm surprised that there is a strong relation.
For graph G, is at most, so for the regular COP number, the line graph, COP number of the line graph is at most the COP number of the graph plus 1. And I would have to look up a reference for that. It's escaping me at the moment. But that's been proved in the literature. And so that's where we got the bound on the COP number of the complete graph and the line graph of the complete graph. Was that your question?
Yeah, thank you.
Yeah. So reference somewhere, sorry.
Okay, well, thank you very much.
Can I ask one last question?
Of course.
Can you say something about the difficulty of computing the versions of COP number that you've talked about?
So some of my co-authors worked on algorithm stuff. So we do have a section in the algorithms on an algorithm of computing the surrounding COP number. And I know there's algorithms in the literature for the regular COP number, but I didn't work on that part of the paper myself, so I'd have to refer you to our paper for more information on that. Sorry, Brendan.
No problem. Nice talk.
Thank you.
Okay, are there any other questions? So if not, then let's unmute themselves and clap again for a very nice talk.